Hi, this is the first video tutorial on Shape version 5 that deals with modifiers. Modifiers are a very important part of Shape, and they are part of the properties of any object and determine mainly their geometry, velocity field, density distribution, and other properties of every object. So we're going to go into quite a bit of detail about this in several parts, and this is the first part on modifiers. Let's begin with a new object creating our traditional sphere, and we will give it a certain radius, let's say 60 units, and change the name to sphere, or let's say bipolar, because we are going to modify it, and go to the modifier panel, add a squeeze modifier to give it some structure, and we're not going to look into the geometry modifiers right now. This will be in a later tutorial, but we're going to look at physical modifiers such as density and temperature, which work the same way. And let's look at the density modifier first. Now, when we select any of the modifiers, its properties show at the bottom of the modifier list, and each of them is a little bit different. The density modifiers has a name field, whether it's enabled or disabled, so you can switch on and off any modifier at any time without destroying them for later use. You will have the first edit panel, which deals with the Gizmo, which basically determines the direction in which this modifier is acting. We will have a closer look at that later. And there's a factor F0 which multiplies everything, the magnitude of the density in this case, by this factor. The magnitude as a function of coordinates is given by editing the magnitude. We click on the Edit Magnitude button, and we get a new dialog where we have access to a graph which determines how the density will change as a function of coordinates. And the F0 factor is reflected again in this panel. So everything that will be set up in this graph will be multiplied by this factor. Of course, it is set to 1 by default. And as an initial function, we have a quick mode. There are several modes to select from: the quick mode, the custom mode, and the analytic mode. The quick mode gives a fast and simple equation, a preset equation with several coefficients that determine how the density changes as a function of distance from the center of the object. Not in word coordinates, but in local coordinates of the object. So we have a linear term which is given by the constant a, a constant term from the constant a, and then a linear term determined by the constant b, and r as the distance, and r0 is the scaling factor, which is given at the bottom of the list of parameters. And then there's a power law term which has the constants c and d. So we can, for example, set a Hubble law by setting a to 0, b to something like say we want 50 kilometers at a distance of 60 units, then we are get a linearly increasing function. If we add a nonlinear term, say let's try 10 and 2, we have a curved function, and so on. Note that this is radially outward increasing density. To get something that goes down radially, we could set, for example, an exponent of -2, the linear term, set it to 0, and then we have a polar that goes down with distance. Okay, the custom mode gives a bit more flexibility. Here you get a graph for each of the coordinates. Now you have a selection of coordinate systems, Cartesian, so in x, y, and z, spherical, r, theta, and phi, where theta is the angle from the pole, that is latitude, and phi, and theta is the angle along the equator. These angles are given in degrees. Now, these graphs are handled as usual. You have two options: either provide an analytic function or a point function where you set points manually, starting, say, at you right click somewhere on the graph and click on add point, and at another position, so you get a sequence of points that you can manually edit. If you need a bigger range, you can either grab one of these and drag them outside of the graph and then reset the graph here at the top with these two arrows. Click on one of these points and then with the right mouse button, and then set points. Say we go up to, we're looking at 60, and then the emission should be, the density should be 0.1, and then reset the graph, and then we have our distribution up to the maximum radius our object has. We can grab one of the points and modify it, change it, take it up and down, and thereby make a detailed graph by hand. That is as a function of r. Of course, we can do the same thing in any of the other coordinates. Note, however, that the way the density is now calculated is by multiplying all these graphs together. The end result will be nr times n theta times nz in this case, times the f0 factor. Now the other option is to use an analytic function. Select analytic, then click on the function tab, and here you can insert any function you want, such as let's say, now important is to note that in these functions x is always the variable that you're looking at. You can then use x0 as a constant, and let's say an exponent of -2, and hit enter. X is the variable for all of these. This is to keep the same variable for all, otherwise it would be very complicated. Now this remains at 0 level because we have not yet set our x0 constant. Now we go to the constant tab, and the x0 constant will appear, and we give it a value like 60, that's the size of the object. Then we hit enter and our function is set. We could add another constant, like say a times this, and enter, and now the constant a will also appear, and we'll give the value, let's say 0.3, and then our function appears again. Okay. For the same happens when you use other coordinate systems. You can switch between one and the other, and your function will remain here. Okay, let's see what we get as a result in the rendering. Note that in the basic renderer, our density is squared. What we get at the end, in the end, is a square of the density as a rendering, mimicking an ionized gas, but this can be changed in the physics setup. We will get to that later. Now we should make this object not a volume-filled bipolar, rather a shell. Therefore we will add a shell modifier and edit that modifier, make it a bit thicker. That's maybe too much. Okay, now we have a nice shell volume instead of a volume-filled bipolar, which is what we have here as a result. Since we are using 1 over r squared density, we get a very bright point at the middle. This should be now should be a nice shell. Okay, right, with increased density at the equator near the center of the object. We can change this display a little bit. We will get into that later, but it's okay for you to see these details, these modifiers here being used. Okay. Now here we have our nice shell with the density decreasing towards larger distances. Now we can make this a bit more sophisticated by adding texture, filamentary texture to the density. Therefore we can click and edit the texture, which is the button down there in the modifier, density modifiers parameter panel, and this texture editor window appears, and here we click on add. We have a selection of noise textures, filamentary textures that can be selected from. Let's select the sparse convolution. Now we have a parameter panel down here, and for this case we will use a small scale, so there's some interesting structure and an exponent of order 20. Now we have these nice filaments here. Let's increase the frequency a bit. Right. Now these offsets, X, Y, and Z offsets, basically determine where this 3D pattern of noise is located. Let's change this, and the whole pattern changes. You can go through this pattern using this slider along the Z direction. This is basically the cube that will be applied to the whole 3D cube that we are looking at, and the object cuts out whatever volume it occupies. If we now render this, we should get a filamentary structure of the bipolar. Right, there you go. Now we can superimpose several of these modifiers, like density. Sometimes it is useful to superimpose different coordinate systems. One part of the distribution might be given in spherical coordinates, the other one in cylindrical coordinates. So we can actually say make a copy, click on copy and then paste. And then we have two options. One is instance and copy. If you choose instance, then these two modifiers will always stay the same. But that makes sense only when we copy them between different objects, which is possible. We could have clicked on copy like now and then go to another object and click paste, and then the instance option would make these two modifiers always the same. Changing one will change the other. If we select copy, then we will have independent modifiers which start out to be the same but can be changed independently. Okay, here we want them independent. In this second modifier we could store the texture, for example, as a possible application. Here we already have the texture and enable it in here, and then call this modifier texture, so we can easily identify it and move it up to stay together, have the two density modifiers stay together. And then now let's see what we get. Now we have the texture applied. Could have done this also in the first modifier, but this is for demonstration only. If we now switch off this second modifier, I'll disable it and re-render, then our object is smooth again. So we can actually do complicated operations to get a more complex density structure. Thank you.